Hello. In this particular video, what we are going to learn is that how we can deduce the value of the universal gravitational constant, that is the value of G. If you have watched my previous video, I have already mentioned that this particular G was calculated by Henry Cavendish, an English mathematician who finally arrived at the value of G. If I take precisely how Henry Cavendish calculated by the use of torsion, it would be a little bit longer. I mean to say a little bit more into mathematical calculations. We are not going to do that. What we are going to do is that we are going to stick to the basic idea of Newton's mechanics. We are going to take the formula F equals to G m1 m2 whole divided by r squared, and we are going to deduce this value. Now, before going to deduce this value, what I am going to show you is that because we are taking a different process, so we would be calculating, or rather we would be taking the value of moon and earth. Yes, the value of moon and earth as it is. So if I just write it over here, the mass of moon, which we already know, we are not going into deduction and all those complications. We are just writing the value. The mass of moon is 7.35 multiplied by 10 to the power 22 kilograms. This is the mass of moon, which we already know as it is. And we also know, and we have deduced it, that from my previous video, you can find the value the mass of earth. So the value is 5.972 whole multiplied by 10 to the power 24 kilograms. These are the two values that we already know. We already know those values. Now, for example, if I draw a very simple figure which would make things clear for you, here is our earth and here is our moon. So we will just take simple conventions. I will just write E for earth and M for moon. And I will just give two values as M1 and M2. And what we are going to find out is the force. Is the force acting between earth and moon. So our main question is that we have to calculate the force. We already know the distance between earth and moon, which we are going to write it as we go forward with the deduction. So currently I am just taking the initial, the basic idea and the equation of Isaac Newton. F equals to G m1 m2 whole divided by r squared. All we need to calculate is this. All these values are given. Currently, to keep the equations and the length a little bit shorter, I won't be writing the values of Newton meter square, second square, all those things in this equation. But I am going to come back to the values because that is the most important thing which mostly people miss and the students miss out. So I will just put it across. We know this is the value of G, 6.67 into 10 to the power minus 11. So I just put it as it is. And just for the first time, I write it just in small Newton meters per kilogram squared. Right? Multiplied by, I will write the mass of earth. That is the mass of earth which is already given. I will just write it for 5.972. There's a dot, mind it. Multiplied by 10 to the power 24. 10 to the power 22. I'm so sorry. It's 10 to the power 22. Just to check in from here, it's 10 to the power... I'm so sorry. It would be 10 to the power 24. Yeah, it's Earth is 24, Moon is 22. And this is multiplied by 7.35 multiplied by 10 to the power 22 kilograms. I'm omitting right at this moment. Now, whole this would be multiplied by the distance. This is the distance. I mention it as D. Now, when I'm writing D, generally what I have to do, I have to convert this D from million kilometer to meter, because this is meter. So mind it, the students mostly make this error that they are not converting them to a single unit. If you don't convert it into a single unit, it become a problem. So what I will do is the distance between earth and moon, which we already know as 3.84 multiplied by, I will write it in million kilometers, so it will become 10 to the power 5. Then I will convert it into meter, and that is 1000 meters. Makes the kilometers. So this one would be 3, this one would be 5. So in total, if I write the distance, it would be 3.84 multiplied by 10 to the power 8. So 5 plus 3, 8 meters. And similarly, just to put it in a different color so that it becomes easier for you to understand. So now we have converted it into meter. What we can do is just write in small in denominators as 3.84 multiplied by 10 to the power 8 meter whole squared, because it is r squared. This is the distance which is squared, so we will put it as. So what we have done is that from million kilometer to meter, I have converted it. Without this conversion, things become difficult. Now you see, what I will do particularly is that I will show you how the values really change. This is Newton meters, right? So I write it as Newton meter squared by kilogram squared, obviously, kg squared, right? Whole multiplied by, this is kilogram, this is kilogram, this is kilogram. So it becomes kilogram squared, right? This becomes kilogram squared, whole divided by meter squared. So this is entirely divided by meter squared. Now you see what actually it gives to. So what we find over here is that this meter squared gets cancelled out. This kilogram squared, this kilogram gets cancelled out. And what we get is the force. That is, the value of the force is Newton, right? So now if I can rewrite the formula, or rather the calculation, which is over here, what I get, I'll just try to be very precise, not to expand it more. Because this is the first phase, we need to go to the second phase. 6.67 whole divided in multiplied by 10 to the power 11. This is within braces. Multiplied by 6. I'm taking it 6 because this is almost 6, 5.97. So I can just write it as 6 into 10 to the power 24. Multiplied by 7.35, 10 to the power 22, which is the mass of the moon, whole divided by 3.84 multiplied by 10 to the power 8. So we convert it into meters. I'm not writing the units right now because ultimately eventually it will come to newtons. So if I calculate it, it would come to 19 point something like 86064 ... I'm not precisely mentioning that. Whole divided by 10 to the power 19 newtons. So I've shifted the decimals to here. It becomes to 1.986064, and this shifts to 10 to the power 20 Newton. Now what we have done over here is that now I can further reduce it just for the convenience part, and I make it as 2. Yeah, 1.9 we can always mention it as 2. So 2 into 10 to the power 20 newtons. This is the force which we calculate. So I can just put it in a very brief manner, 10 into 10 to the power 20 newtons. So between the earth and the moon, this is the force which we just calculated. Very simple. All we need to mention over is here that we really convert it and we get the unit of force, and we get it as the Newton. So this is part 1. Now we will come to the second part. This is what we have done. We have calculated the force, that is how much is the force between earth and moon. Now if you kindly excuse me for turning the page, because it would take me to the next phase, is that what we will do is that we will, in the same way, we are going to substitute all those values which we have calculated earlier into the basic Newtonian formula. So here is the formula which I get over here. I'm just going to write the basic part. We already have done that. That is F equals to G m1 m2 whole divided by r squared. Now we know this part, right? Force we have calculated. It is 2 into 10 to the power 20 newtons. G is our basic idea. We are striving to calculate G. That is the universal gravitational constant. So I put a question mark. This is known, this is known, this is known. Simple calculation would lead to this. So I can write is that 2 into 10 to the power 20. Again, I'm omitting the values right at this moment. I will come to this part. Equals to G, which we want to calculate, times 5.97, which I have already shown. It can be written as 6 into 10 to the power 24 multiplied by 7.4. It is 10 to the power 22 Let me just quickly see what is yeah. So moon is 22, Earth is 24. This is a this is a little bit confusing one, right? So I get it, and this is again whole divided by 3.85 multiplied by, I am putting it currently as 10 to the power 5 kilometers squared, because we will do another small conversion which will make things clear. Now if you see that if I write G, say I cross multiply and bring G out over here, because G is what we are calculating. So we can put it as 29.645, right, multiplied by 10 to the power 20. So we are doing this cross multiplication, multiplied by 10 to the power 8 squared. So I have to write again 10 to the power 8. So I'm taking this 5 plus 3, 8 over there, Newton meter squared. For the time being, let me write this one, whole divided by, then I bring things down, 44.4 multiplied by 10 to the power 24 multiplied by 10 to the power 22 kilogram squared, right? So we do this, right? And we take this over, this is over here 20 to the power 24, so it yields to this. Now I will show you how this would turn into, because again there is a small unit conversion which we just need to note very importantly. Now we know that 1 Newton equals to 1 kilogram meter per second squared. This we already know, right? Now what I can do is that if I put the values over here, what it would eventually result to. So what it will eventually result to, say for example, if I put the value over here, so 1 Newton equals to 1 kilogram meter squared. So what I get over here is that I can write kilogram meter squared, kilogram meter by squared, multiplied by, I get over here is meter, right? So I am replacing this Newton, this entire Newton by a uniform unit, that is kilogram meter per second squared, whole divided by m squared, and then I again divide entirely by kg squared. We divide it by kg squared. Now you see what it happens. This and this will lead to meter cube. 2 plus 1, 3, right? Kilogram and kilogram gets cancelled out. So we are left with 1 kilogram. This kilogram, once it goes up over here, it will become kilogram minus 1. And this second square, once it goes up, it will become s minus 2. Now you see, there is an international unit in gravitational constant which measures 6.777 m cube kg minus 1 s minus 2. This is one part of the gravitational constant which we can write. Also we can write 6.77, that is what we are deducing, 6.67 minus 10 to the power 11 Newton meter squared kilogram squared. So this is another. So this is precisely m cube kg minus 1 followed by s minus 2. This is measured in terms of what I would say international standard. That is international. We call it as SI unit. Right? So now from here, you see what I have done. Newton had been replaced. Meter square is as it is. Second square is as it is. Kilogram square gets cancelled out, and if it goes up, it becomes negative. Second becomes negative, and this is what is called SI unit. Now let me just from this particular equation, just let me quickly derive it, because I'm not going to spend more time in writing all those parts, because you already know, you can do it from your own. So just to mention the important part, this would result to, I mean to say, this one will result to, if you calculate it, it would eventually come to 0.6678 multiplied by 10 to the power minus 10 Newton meter squared kilogram squared, which is the 1 unit. And if I write it in this way, if I shift the 0, so it becomes 6.678 minus 10 to the power 10 becomes 11. And I can also write it as m cube kilogram minus 1 second minus 2. So finally what we have done is that this is the gravitational constant which we have deduced from the equations. This is also the gravitational constant. So it can be 0.66, it can be 0.67, minor difference. This one doesn't matter, this would be 0.67. So this is how we have arrived at the conclusion. So remember that in the SI unit, we can write it as meter cube, kg minus 1 and s minus 2. And we can also write it as Newton meter squared per kilogram squared. This is also right, this is also right. So this is what we have done. So we have finally arrived at the conclusion. It is 6.67 and the units can be either this, either that. So let me just summarize what we have learned. I will just turn the page over and go back to my previous calculation so that you can understand it. From this part, what we have calculated is that we have given the value of mass of moon and the mass of earth. What we calculated is the value, is the force between the earth and the moon, and this is how we did it. Two important points is that we converted the distance into meters, because this is meter, it has to be in equal unit. Newton meter squared, kilogram squared gets cancelled out, and here we see that we have finally arrived at Newton, which is the value of the force, and the force between earth and moon is 2 multiplied by 10 to the power 20 Newton, and this is what we have calculated. Coming to the second part, what we have done precisely is that we have taken the same formula F equals to G m1 m2, and this m1 m2 and r squared are already given in the previous equation. Force we already know, we have to calculate the value of G. Now 1 Newton equals to 1 kilogram meters per second square. What we have got here is a Newton multiplied by meter. Below we have got kilogram squared. All gets cancelled out, and what we get is a unit which we call as international standard. Multiplying and solving over these equations, which we can later do, it results to 0.67, which shifted to the decimal becomes 6.67 or 6.66. Minor difference, doesn't matter. So this is how we can deduce Newton's gravitational constant, which was deduced in a different way by Henry Cavendish. This is the standard unit by which we get the negative of kilograms and s. Because it becomes a little bit complicated to calculate, generally for physics students, this is taken as the value Newton's meter squared per kilogram squared. Thank you very much for watching the video. Stay happy, stay safe, and watch out for more videos in few days more. Thank you very much.